We'll be discussing chemical reaction rates, sort of an introduction to them in this video. The supporting topics are understanding concentrations, chemical reactions, and physical states of matter. In order for a chemical reaction to occur, collision theory describes the scenario, the setup, the characteristics, I guess, of what have to happen in order for reactants to form products. It turns out that reactants have to actually collide with each other. If you think about your atoms as having to get together to make a molecule, then they need to be in close proximity. Whoops, that last one needed to be blue. Let's redraw my molecule. Bloop and bloop. They need to be in close proximity to actually form those new bonds necessary to make the new compound. Or if they're breaking bonds, they need to be in close proximity to do that as well. There's a cost for doing each reaction, and that's called the activation energy. And just think about this as the dollars for doing the reaction. It's kind of like going to an amusement park. You have to pay to get in to ride the roller coaster. So there's a cost for participating in that activity, and reactions, there's a particular cost associated with doing a particular reaction. The other thing that ends up being important is the correct orientation of the reactants. And you need all of these things in order to produce products. You can think about this kind of like Legos. If you think about just a pile of random Legos, you haven't really made anything, but in order to produce something from those Legos, in order to create something, to build something, you have to put the Legos in close proximity to each other, and in fact you kind of have to shove them together. It takes a little bit of energy to get them together and attached, and then it takes a lot of energy to get them apart. And then they need to be correctly oriented, because if they're not, then they don't actually attach to one another. And if you were so inclined, you could use Legos to build, hey, a car. Just kidding. Somebody did, though. It took a lot of energy. I think the cost of building that car was quite big. Okay, so when we talk about reactions, we can also draw an energy diagram for them to describe what's happening. So any particular set of reactants has a particular energy that we start with. So over here we've got our reactants, and they're starting about there. The activation energy is that cost of doing the reaction that the reactants have to get over in order to scoot on down there to products. So this difference in energy between here and here, that's the cost of doing the reaction. It's called the activation energy. If a particular set of reactants doesn't have the activation energy, they don't have the money in their wallet, then they don't get over the barrier and they don't make products. They just go back to being reactants. There's an overall energy change for the reaction. In this case, we started with our reactants at this level, and we ended with our products down here. And so overall, our energy dropped. We went from reactants at a higher energy to products at a lower energy. And because that's the case, energy overall left the system. So if we started a higher energy and we ended a lower energy, energy is leaving the system. That's considered an exothermic process, or an exothermic reaction. If instead of this particular diagram that I have here, I'm just going to erase all my stuff on here so I can draw it and make it more clear for you. Boop. If instead of my reactants, my products being below my reactants, if instead my reaction had ended, say, here, and my products were up here, then in that case, the activation energy is still the same, because the reactants still have the same cost to pay. But in this case, I end up at a higher energy than I started with. And so my overall energy change was rising up. And so energy had to come into the system. Energy goes in to the system. overall in order for this reaction to occur, and that's considered an endothermic reaction. So, endothermic reactions means you have energy coming in and your products end up at a higher energy than your reactants were. And exothermic reactions, energy leaves the system and my products end up at a lower energy than my reactants originally were. You can make reactions go faster. You can increase that rate. If we think about, just pause for a moment and review what we know to be true about what makes a reaction occur. We have to have things collide. They have to have a certain amount of energy to pay the cost of doing the reaction, and they have to have the correct orientation. So if you have a physical state of matter like a gas, where you have a lot of degrees of freedom and a lot of contact area, then you probably get a faster reaction than if you have two solid lumps sitting right next to each other, where there's not as much interaction between your particles and not as many opportunities for collisions. If you add heat, we know from our discussion of gases that adding heat generally makes particles move faster. If they're moving faster, then they're more likely to run into each other, which means you have more collisions, and it's more likely that you'll have a collision with enough energy and the correct orientation to make products. You could also add a catalyst. So I'm going to go backwards here for just a sec to my reaction energy diagram. And I'm going to show you what a catalyst looks like. So when you have a catalyst, it provides an alternative reaction energy pathway to get from reactants to products. And you'll notice what's key about this is that now my activation energy, or my E sub A, is much lower. So this red pathway is the reaction pathway with a catalyst. And we see, whoa, the cost of the reaction just went down. It's like a sale. And now suddenly, those collisions that weren't quite cutting it before suddenly are producing products. So if you want a reaction to go faster and you have a catalyst available, lowering the activation energy will make things speed up. The last thing you can do is increase the concentrations of your reactants, because the more stuff you have, the more likely it is that they're going to run into each other and collide and actually produce products. So, which reaction will go faster? If you have a reaction with a reactant concentration of 0.1 molar versus one with a reactant concentration of 0.2 molar, what do you think? Well, 0.2 molar is a higher concentration. You've got more stuff, so that's likely going to be the faster reaction. If we have a reaction with a high activation energy versus one with a low activation energy, I think about this as kind of like a pair of shoes. One costs, I don't know, let's say $1,000, and another one costs $5. How many people do you think you're going to see in the $1,000 pair of shoes? Not very many. How many might you see in the $5 pair of shoes? Quite a few. So that low activation energy reaction, that's going to go faster. A reaction with solid reactants versus one with liquid reactants, we know that liquids have better contact, better surface area, better ability to mix with one another and to have their particles come into contact and collide, so that will go faster. And then a reaction with a low temperature, so molecules are moving kind of slow, versus one with a high temperature, where the molecules are moving super fast. Well, those super fast molecules, they're moving around more, which means they're more likely to run into each other. Plus, when you think about driving in your car, if you're going really slow and you hit somebody, there's not a lot of damage to your vehicle. There's not a lot of energy in that collision. Versus if you're going 60 miles per hour down the freeway and you collide with somebody else who's going 60 miles per hour down the freeway, there's a lot of energy in that collision and a lot of damage. Now, if we use this metaphor to understand what's happening with our reactants, the more energy these guys have when they collide, the better, because the more likely it is that they'll have enough energy to get over that activation energy barrier.